Balaji to enlighten us on the topic past, present and future of digital agriculture. Please, sir.
Good morning. Good morning. All right. Very good number. And I assume rest in the hall are faculty. Is that fair to say? All right. Okay. All right. Very good. Well, thank you for taking time from your busy schedules to come and listen to what I have to say in the next 45 minutes or so. What I'm going to share with you is how precision agriculture, or what's now broadly referred to as digital agriculture, has evolved. That's what I'm going to talk about. Because the majority of the people who are sitting in the audience are students, I have a special challenge for you. And that has to do with ability to translate data into information, into decisions. Okay, so that would be the overarching theme of my presentation. How do we translate data into information so that we can make better decisions? All right, keep that theme in your mind. So let me start by asking you to imagine. I want you to imagine how agriculture may look like in, let's say, 30 years from now. What would be your answer? I kind of hear a murmur of, sir, digital agriculture. You take it for granted it's going to be digital agriculture? So the funny thing is that none of us have a crystal ball. A crystal ball is it's for centuries people look at crystal ball to look into the future. Anybody has a crystal ball here? No? We don't have a crystal ball, right? So looking into the future is very hard. It's very hard. So I'm not here to tell you what future is going to be because I'm not that smart. But how about we look into our past and see how we have come to where we are today, right? So here's a picture for you. What do you think this picture is? You have to speak louder. Raise your hand if you want to tell me. What do you think this picture is? Anybody? A computer. I hear answer computer. And it has wheels. So this is a mobile computer then? Let me give you a hint. This in future became the backbone of precision agriculture. Any more guesses? Well, let me tell you. This is the first GPS receiver that was put together in 1976. This is the first one. This was so large that maybe 6 or 10 systems will fit in a room like this. So here's another question. And it's very hard for me, by the way, it's very hard for me to stand here and talk because I have a propensity to walk when I talk. So, but that's okay. I'll stick to the podium. If you have a lapel microphone, oh wow! I always like to make sure I'm talking to an engaged audience, because if I'm talking and you're not listening, then there's no reason for me to be talking, right? Okay, so this is the first GPS receiver that happened in 1976. Now tell me, how many years did it take to go from here to here? You can hold the GPS chip today at the tip of your finger, right? You can. How many of you use cell phones? Oh, everybody uses a cell phone. So, if you bought a cell phone in year 2000, I hope nobody's carrying a cell phone that was bought in the year 2000, right? It has a GPS chip in it. So everybody uses the GPS chip. So my question is, how many years did you think it took to go from that massive GPS receiver to something that you can hold on the tip of your finger? Take a guess. 30 years. No, it did not take that much time. In less than 20 years of time, we went from something that large to something that you can hold at the tip of your finger. And everybody on the planet uses GPS chip today, right? In fact, very soon, the number of cell phones are going to surpass the number of people on the planet. Do you know people who carry 2 cell phones? Do you know people who carry 3 cell phones? Okay? Or they have multiple chips in the same cell phone, right? GPS is omnipresent. So, this is a great example to illustrate how we're going to change in 10 years or 20 years. We tend to underestimate our potential. Okay? We tend to underestimate our potential. And that's not a bad thing. You do not want to overestimate, right? You do not want to overestimate. Now, this is the first GPS mobile unit, among the very first ones that was used in war by our military. Okay? See how it looks? And I've been using GPS for about 30 years, and this is the unit that I used to mimic exactly how they were doing. So I'm carrying a GPS unit. Here's a tackle box, or a toolbox. Inside the toolbox are deep cycle batteries to make sure the GPS is powered all the time. Back then, so this picture is coming from somewhere in 90s. I have a black and white Fujitsu pen tablet. It's not like an iPad or iPad today. This thing was 2.5 kilos. Okay, so I'm carrying batteries, I'm carrying GPS, I'm carrying this 2.5 kilo. Look at my wristband. I have a data logger. Things were not together. I had a data logger, and I'm using this Minolta chlorophyll meter, and I'm going to plants and recording their readings everywhere. Our field sizes, I know some people say, you know, you are coming from a large-scale farming system. I walked 100 acres. This was in 90s, trying to create a spatial variability map of nitrogen to see where plants are happy with nitrogen, where plants are deficient in nitrogen, so I can create a spatial map. The farmer I was working with said, "You're crazy." I said, "I know it." But these were the growing pains at that time because we didn't have integrated technology. We wanted to know how much variability existed. And so this was a lot of hard work that went into that. Now, there's one piece of technology that is used worldwide are tractors. In fact, how many of you know that India has one of the largest densities of tractors in the world? Largest density of tractors. Now, I also understand that not all tractors are used for farming. A lot of them are used for transportation, so I understand that part. But this unit, which is totally autonomous, do you see a person there? No? You don't even have a cab, right? You don't even have a cab. This came out commercially in 2017, so this is 5-year-old technology. Now, this is a large machinery. Of course, it'll fit only maybe one in this room. But a similar model where you have smaller machinery that can be used as swarms that will go in the small-scale farming systems just like this would go in the large-scale farming systems. Just 4 weeks back, I was visiting a farmer in Kansas, and this is the farmer right here, this person, he's the farmer. This is his planter. This planter is 54 rows planter. In 30 seconds, it can plant 1 acre. Well, you're thinking, oh wow, that's great. How many acres is he farming? This particular farmer is farming 45,000 acres. So let me give you a little bit of statistic, okay? Because things look greener on the other side of fence. Let me give you a little bit of statistic. So the average farm size, mathematically, it's about 998 acres where I am. Okay, so let's call it 1,000 acres, okay? 1,000 acres. But typically when I'm working with the farmers, they have about 2,200 acres is a very common size of farm, 2,200 acres. How many people does it take to farm 2,200 acres? Just a guess. You may be right, wrong, doesn't matter. I'm not here to judge you. How many people will it take to farm 2,200 acres? 5 to 10 people? Anybody else? More? Less? 2 people? Actually, you happen to be right. So a typical farm, you have the farmer and you have the farm manager, 2 people. And then you have about 6 to 8, so you're also right. Then you have about 6 to 8 seasonal employees. So a team of about 8 or 10 people who would farm the typical farm, because labor is expensive. Labor is expensive. So the funny thing is, if there's a leak in my faucet, like a kitchen faucet or something like that, if I call a plumber, for the plumber to come and just tell me that your faucet is leaking, what the problem is, he bills me $100 just to come and tell me that it's leaking. And then, so it's called diagnostic fee. It's called diagnostic fee. And then they will fix it, and he's going to bill me for time and the parts. Labor is expensive. Hence, gravitation towards machinery. I understand increasingly availability of labor at peak time in farming operations is getting challenging in India and other places as well. So this is a spread of his farm. The circular units that you see, the fields that look like circles, these are actually irrigation systems. So the irrigation system is like an arm that's situated in the middle of the field, and that arm will move like this. And that's why our fields are circular. Everybody makes sense? Right? Makes sense to you? So those are the irrigated fields. So the farmer was telling me that when his dad used to farm, which irrigation is running, how much water he is applying, when is the next irrigation circle will be done. He used to do it in color coding, and he will write everything by hand, and that's an example. Then he took me inside to his office. If you go inside his office, you will have these 90-inch screens, 8 or 10 such screens today, where he monitors digitally. I'm sure many of you may have cameras at home or outside your home property that you can look it up on your phone today, right? Okay? He monitors physically the location of the irrigation system, where it is, how many inches of water it's applying, whether it's running or not running, and where it is in the field, how many days it's going to take. He can monitor everything just by looking at the screen. And he can flip the screen and can do that. Notice the digitization of ag that is slowly happening. Remember how his dad was doing? He was doing it on a piece of paper using a pen, right? So there's not a new function that has been added. It is a simply digitization of the process. What would be a good example in the Indian system? For those who remember, if you were to travel, how would you buy train tickets? Who would remember that? You will have to physically go to the office, right? And you'll have to purchase the ticket. You have to hold it in your hand, right? How are we doing that today? Total digitization, right? In fact, if you want to go personally and buy an air ticket, they charge you more money because there's a human being interacting with you, so you're making expenditure. With me? That's exactly what's happening in agriculture. It's the digitization of the process, right? The question is, how did we get here? Let's go back in history. 1957, how many people were here in this room? Maybe no one. 1957. What about 1957? The first ever satellite was put in space by Russians, Sputnik. 9 months later, United States put their first satellite, Navstar, which later on became part of GPS, Global Positioning Systems. It started, the birth of GPS started in 1957. All right? Let's fast forward. 1983. Now, how many people were around in 83? Quite a few. Quite a few, right? What about 1983? Okay, so you're sharing some example, and I'm talking about GPS and I'm talking about Precision Ag. In 1983, unfortunately, a passenger plane flying over Central Asia deviates from its path. It enters into an airspace of another country, it shoots it down. Very unfortunate. President Ronald Reagan in the US made an announcement within a month that GPS will become available for civilians. 1983. That's a landmark in the history of humankind, because everybody today uses GPS. Everybody. If you're using a cell phone, you're using GPS. So that was a landmark event. Now, I have taught GPS or GIS and remote sensing for the last 25 years. I've taught 3 courses. This is the very first thing we do in our lab. We calculate the error in GPS. Make sure you understand, GPS is full of errors. You don't get to see it, but there are errors. So when I used to run this error analysis, what you have on the x-axis is the easting in meters and the northing, it's a 2-dimension x and y. And notice the circular error prevailable, so 2-dimensional x and y error in those days used to be more than 50 meters. So your one point is here, another GPS point may be outside the building, third point may be over there. You're dancing all over the place. So when you do the circular error analysis, you are about the size of 100 meters. Is that good enough? Would you do agriculture with that? Even is it good enough for your cell phone? Absolutely not. Okay? But those were the days. In fact, I pulled out a paper from IEEE Journal, and they documented that the horizontal positioning was 100 meters, the vertical positioning was more than 150 meters in those days. 150 meters. Today, your airplanes are landing using GPS. If you have a 150 meter error, you can't do anything, right? It was a big change, but was not good enough. Was not good enough. In fact, if you look at the papers, journal papers that were being published in those days, people were excited. Scientists like you and I were excited. Hey, we're going to have GPS that you and I can use. And so engineers are talking about access to GPS. I want to draw your attention to paper number 2. This person, I don't know if you can read it from there, Dr. Brad Parkinson. Has anybody heard the name of Dr. Brad Parkinson? Maybe not. Father of GPS, Dr. Brad Parkinson. In fact, just before pandemic, COVID happened, him and his 3 other colleagues were recognized with £1 million award by Queen Elizabeth for their contribution to developing GPS, which is now omnipresent. It's not an exaggeration, it's omnipresent. You go to Africa, you go to Latin America, you come to South Asia, it's everywhere. So they were given this a massive award, of course, very deserving for this. Why am I telling you about Dr. Brad Parkinson? 1, because he's the father of GPS, and 2, I was privileged to work very closely with him. So in 2011, I was appointed to the NASA board, to the U.S. Presidential Advisory Board for NASA to work on GPS policy, that how we can use GPS in agriculture. So I'm at one of these board meetings, and that's Dr. Parkinson right there. Okay, this is myself. And I was appointed for 2 years, and my appointment was extended again for another 2 years. So I was on the NASA board for 4 years, learned tremendously about GPS and how it works, but also a very strong vocal voice that we need high-resolution GPS for agriculture. And today it has happened. Okay? In fact, I want to draw your attention to the person who's sitting right next to me at this meeting, Dr. Ron Hatch. He was the brains behind using 2 bands of GPS. Okay, so GPS has multiple bands. He was able to use
dual frequency to really reduce the errors from 50 meters to 10 meters to 5 meters to how much? Decimeter. That's Dr. Ron Hatch. He's no more. Dr. Parkinson is still around. And so that was Ron Hatch who did that massive amount of work. And so what happened that today, and I want to highlight another individual here, is Dr. Pierre Robert. Dr. Pierre Robert. Who was he? He passed away in 2004. Dr. Pierre Robert is the father of precision agriculture. Late Dr. Pierre Robert. He was a professor at University of Minnesota, where he founded the very first Precision Ag Center. Now there are so many other centers today, including ours, but he was the first one who did that. And just like happens with any technology, a group of friends sitting in a bar after a conference like this were talking over a beer and cocktail snacks. And they were thinking, what if? What if GPS ever becomes available for agriculture? And so one of the friends started to scribble on a piece of napkin. I'm not exaggerating. That's exactly how it happened, on a piece of napkin. And this is something what they drew, which later on became the most publicized schematic on the planet of precision agriculture. IPNI, International Plant Nutrition Institute, put that from the piece of napkin and used a graphic designer to illustrate that if GPS ever becomes accessible to agriculture, this is how it may look like. That every operation on farm will be connected to global positioning system. This is reality today. Maybe not in India, but in North America and many other advanced nations, this is reality. Every operation is connected to GPS. Okay? I want to talk about Gartner Hype Cycle. How many of you have heard about Gartner Hype Cycle? Okay, Dr. Rao has, not surprised. So this is a very interesting phenomenon. So what I have on the x-axis is time. And on the y-axis, I have expectations. So this would be interesting for those who don't know this, particularly for the young minds. So you have time and you have expectations. So whenever there is an innovation or a technology trigger, whenever there's an innovation, right, what happens? If something was innovated, whatever that might be, it creates expectations, right? So I'm talking about GPS, right? So GPS became used for civilians, and so it came with expectations. So what happens? The expectations rise rapidly. It rises rapidly. Hey, we can do this, we can do this, we can do this, we can do this, right? And it reaches a peak. What happens then? Reality hits, right? And you say, oh my goodness, I can't do this, I can't do this, I cannot do this, I cannot do this. And you're on a slippery slope, and you get to the bottom. That's called the tray of disillusionment. Okay? Now many technologies, that's where they die. They never take off, they die. However, if you can turn the curve, that's when the real progress happens, slope of enlightenment, and then you get to the plateau of productivity. Everybody with me? Okay, all right. Let me give you an example that you can wrap your head around. How about drones? How many of you have heard about drones? I thought so, okay? What happened when drone was launched about 12 years back in the US? What happened? It came with expectations. Hey, forget about satellites. I can fly a drone and get an image, right? Oh, it is the solution to all my imagery challenges. I don't need to worry about satellite. I have very high resolution. It's easy, quick, and cheap. I can do it myself. Oh, it's going to create new jobs. Expectations, 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 right? What happens then? What happened with drone technology? I don't know if you have followed it or not. All of a sudden, people who were involved in that They said, oh my gosh, there are regulations. I just cannot fly drone. I have to abide by the regulations. Oh, I need infrastructure, training, skill. I need software. It takes 24 hours to process an image. Okay, you fly and you get hundreds of images. It takes 24 hours to do that. Oh, I cannot fly on my neighbor farm. Privacy. I cannot fly above you. Privacy. More regulations. And it turned out that if I take an image, I cannot sell it to you. You're not going to give it to me. Why would you pay for it? It's just an image. People needed not just data, but translated into information so that they can make a better decision. If I give you data, it's useless. Get it? What happened in this time? 3 years went by. Drone technology was about to die. Seriously, it was about to die. It was going away. But that's when there was a turning point. Why? Film industry liked it. Real estate industry liked it. And that's exactly what happened. Regulations were easing up. There was more clarity. People were developing software. They were reducing the processing time. Things were moving in the right direction. There are open source software now. You can go online. You take 100 pictures. You can stitch them together. Maybe if you have a good computer, in 20 minutes. From 24 hours to 20 minutes, right? And there are so many other applications today, utility mappings, wiring mappings, roadways, solving problems. If there's a rail problem or something like that, you know the history. So this is, for those who didn't know, is a classical Gartner hype cycle. Every innovation goes through it. Which innovation I'm talking about today? GPS, right? I'm talking about GPS. So here's the precision agriculture. It started in 1980s. It went really quickly with a Gartner hype cycle, started to come down, but there's a turning point in year 2000. Turning point in year 2000. And in fact, if you look at the curve, that curve has shifted again. Another thing I want to point out, that this picture in the background is not by a coincidence. Precision agriculture is in the stage of infancy. It's just getting started. And the future is with the young minds. What you do with it. To take this technology and run with it. Now we know that it's going to stay. And that's why the young plants. So what happened in year 2000? How many of you are around in year 2000? Come on. A lot of people, right? So what happens in year 2000? Which totally changed the trajectory of precision agriculture. Let me tell you. The reason GPS accuracy was 100 meters was not because that's what the technology can deliver. That was not the reason. It was meant only for military. So signals were locked. In 2000, President Bill Clinton made it into law that selective availability will be removed, right? And so then you do the error analysis, and now your circular error probable is 6 meters. So in year 2000, all of a sudden, accuracy went from 100 meters to half the size of the width of this room. Now we're talking, now it became very exciting for civilian applications, right? Because it's highly. So take a look. This is the data that's coming from NASA. Minus 200 meters, plus 160 meters. Look at the dancing errors. Okay? How large are the errors? 100, 200 meters. On May 2nd, 2000, when President Bill Clinton signed this into law, look what happens to accuracy. Immediately, it becomes highly accurate, more usable for civilian. If you are using your cell phone with 100-meter accuracy and you're trying to go from Hyderabad to Bangalore, sometimes you will be on the road, sometimes you will be in the ditch, sometimes you will be in the field, right? That's not the case. You're always on the road because you have that high level of accuracy. Something else happened. Something else happened. What was that? Wide area augmentation system. This is a satellite-based augmentation system that creates a regional network that gives you additional frequency to further reduce the error. So now, with wide area augmentation system, and by the way, India has deployed that too. IRNSS is over South Asia, okay? And so this is for the North America, and that gives you a much higher level of accuracy. So now you're within 15 feet. Most of the time you're within a feet or two, right? So take a look. We were at 100 meters. When the locking or the encryption was removed, we came down to 15 meters. And when the WAS came into existence, there are a few countries, Japan has it, Europe has it, India has it. Of course, Russia and China have their own entire GPS equivalent system. But for those who have it, their accuracy is 3 meters. So your accuracy is 3 meters. Okay, that's why you're always on the road when you do the navigation. You're not dancing around. So this is where we are, right? This was what the founders of precision agriculture were thinking, that one day we'll get there. And we have. In North America, we have. But they cautioned us. They cautioned us that when farmers, and this is slowly happening in India now, that when farmers start to engage in some form of location-based agriculture, that's what it is. GPS gives you location. It doesn't do anything else. It only gives you location. That once they start farming location-based, that they will be collecting lots and lots and lots of data. And this is exactly what is happening. That as you're doing location-based agriculture, you're collecting tremendous amount of data. This is only example of 4 data layers. I'll give you some more examples. Okay? I'll give you some more examples. So here's a farmer. This is very common. They have a cell phone, and they have, this particular farmer has an iPad unit. Of course, whatever this farmer is doing is connected to GPS, just like your cell phone or equipment, right? Okay. Then the drone that allows you to quantify variability either in soils or crop canopy. This is also happening in India. Fairly common. In some of the states, it has picked up very rapidly, and drones here are being used for actuating spray applications. Okay, so that's a welcome change. That's not happening in the US, but it's happening here. So that's an example of a leapfrog technology, that you took a tool, modified it, and put it to your own application. Okay, so drone we all know about. Wireless sensor networks. They're coming faster than we know, wireless sensor network. Let me give you an example. This is a sensor node that I established in year 2012. Okay? This sensor node is 12 feet tall. Here's a data logger, and take a look, there are 5 cables that are going in the soil. Each cable is connected to a soil moisture sensor. So I'm measuring soil moisture at 5 depths. Okay? And then, here's the data logger, and then there's another cable that going to the top. This is solar panel, and here's the telemetry sensor node. So it dumps the data to the cloud server. Everybody with me? So when you take a picture, where does it go? It goes to the cloud, right? On your Google phone or iPhone or whatever that is. It goes to the cloud. That's exactly what's happening here. This is my precision pivot field. This is a small field, according to our work. This is 22 acres. Now what I have put here is a precision pivot where I have a pivot arm or sprinkler arm that has drop nozzles, okay? 5 feet apart. I can write a program and tell each nozzle how much water to apply as the pivot goes across the field. Everybody understand what I'm talking about? Yeah. Okay? So it can capture how much water I want, where, and when at 5 feet by 5 feet, right? No. So think about it. Everybody is holding a glass. Imagine each one of you are holding a glass of water. Some of you are drinking, some of you are not drinking, right? And these glasses have sensors, okay? So I can ping these sensor within a second, like a sensor node, right? And can immediately find out how much water is needed in each and every glass. Get it? Right? And so then it sends the information to the person to come up with the picture with so much water to refill every glass, right? So I tried to give analogies to break down the complexity and keep it simple. That's what I tried to do. Likewise, I have the technology to deliver how much water I want and where I want and when I want. Where is the sensor? If I don't know where in the field, when in the field, how much water is needed, I need to measure, right? I need to measure. And I can only manage what I can measure. I can only manage what I can measure. So I needed close to 100 sensor nodes. 100 sensor nodes. In 2012, this setup was more than $1,000. So if I even have the money, that's $100,000. No farmer on the planet will ever afford that kind of money for one field, right? And that too on a small field. We did this work. This was research. We did this work. But the change is coming. Technology is changing. I'll show you in a second. But what happens when you're collecting data in X and Y, right? X and Y dimension, and Z depth, X and Y, Z depth, and time T. X and Y, Z depth, and time T. It's a multi-dimensional data set, right? Multi-dimensional data set. And you can measure soil moisture, or for that reason, any property of interest as many times as you want throughout the day to look at what's happening to your soil moisture. You will start accumulating multi-dimensional data sets in hundreds and millions and billions of data points. Can you imagine that? Very quickly, you start collecting millions of data points. And you start collecting millions of data points, then all of a sudden this, what looks like advantageous, what looks like opportunity, immediately becomes a challenge. Because you're sitting on a heap of data that you don't know, how do I translate the data into information, into decision? And that's what I would like to challenge all the young minds who are sitting in there. Learn GIS if you want to be on the wave of future of agriculture. I was very pleased to see when your Vice Chancellor was showing me what the university has accomplished in the last 8 years. There's a remote sensing lab here, there's a GIS lab here. Take advantage of that. Learn R. How many of you are learning R? Learn R. There's one hand went up. Good job. Learn R. Or learn Python. Okay? And for the faculty members who are sitting here, think about adding these courses into your curriculum. Okay? GIS, remote sensing, R, statistical package, it's open source, and Python, so that you can do the scripting in R. Geostatistics. This data you cannot analyze with classical statistics. It's a location-based data. You cannot run classical statistics. You will have the type 1 error. You can't do that. So you need geostatistics. If you are empowered with those 5 skill sets, let me tell you, you are in big demand. Right now, there are 54,000 jobs in precision agriculture in the U.S. alone that we can't fill because the skill sets are missing. And agriculture in India are also changing very rapidly because in some cases here, the farmers might be making the investment, but here, private companies are creating those sensor nodes and collecting the data, so they need young minds with those skill sets, with much higher salaries, to be able to translate data into information, into decision. How would you do that? There's no magic. You have to develop algorithms. And that's where the GIS and GPS and remote sensing, R, Python, and geostatistics will play a critical role for you to be able to get there. So I want you to look at the bottom of my slide here. I'm not showing you leaves, I'm showing you data. I'm showing you numbers. And that's exactly what is happening. That as agriculture is changing, we're collecting lots and lots and lots of data. That's what the challenge is. So what is it that we're trying to do? We grow plants where? On soil, right? I mean, there are hydroponics, aquaponics, and others, but primarily on soils. And soils are heterogeneous, and so we're quantifying the variability. How do we manage that variability? We use inputs, right? We use inputs. But we can only do so far because we all know Mother Nature is the biggest driver. And so there's a lot of work that's happening in weather. We're collecting lots and lots and lots of data, using technology to do the crop management. That's a full circle. That's a full circle. That's exactly what we're trying to do, to make agriculture more productive, more efficient, more profitable, and doing all of that in a sustainable manner. Those are the 4 goals of digital agriculture. More productive, more efficient, more profitable, and doing all that in a sustainable manner. So this is the past, and here's the future. These are microsensors are coming in. My lab is part of a large project, and there are several other laboratories that are working on the next generation of sensors. These are small. And I talked about scale-independent precision agriculture in November at the keynote that your Vice Chancellor hosted, the Indian Agronomy Conference, the 5th Indian Agronomy Conference that I was part of. These sensors are small, and you can literally take these sensors and just throw them in the field and forget about them. In fact, the project that we're working on, these sensors are made out of biodegradable material. So after 200 days, they start to break down, and they literally dissolve in the soil. These sensors are being printed just like you print newspaper. So when totally commercialized, you can print hundreds and thousands and millions of these sensors. The price of the sensor, we're targeting less than $1, so we're talking maybe 10 rupees or 20 rupees or something like that. So it would not be the technology that's holding us back. It's the data. Imagine, be careful. When we have access to this technology, what happens? How do we translate that data into decision? That's a big challenge, and that's what groups like mine in Kansas State and other laboratories are dealing with right now. This is the sensor that we're talking about. This sensor has no battery. It's very tiny. Okay? It's passive, so it's sleeping all the time. When we ping it, it wakes up for a millisecond, does their measurement, goes back to sleep. Our targeted cost is $1 per unit. There are other laboratories that are working on, so that's what I've shown you, work of my lab, is in situ soil sensor. So you don't have to take a disruptive soil sample. Nobody has to go to the soil and break it down and take the soil sample. It's an in situ soil sample. What some other labs are working on are in-plant sensor that you can actually spray on the plant or paste it on the plant to start taking plant measurements of your interest, diagnostic measure. In fact, there was an experiment done by NASA in year 2000, so this is 20 years old, where they demonstrated that you can attach the sensor to the leaf and then write a program that whenever the turgor pressure of the leaf goes down, it sends you a text message. The plant is communicating with you, come water me. How about that, right? Come water me. Think about innovation. That's what I want to challenge you. Think about innovation. How do you keep this innovation inexpensive, cheap, so that it's scale independent, not just for large farmer, but for small farmer? And I talked extensively about frugal innovation, something that can be used for haves and have-not. Can anybody give me an example? What's a great example worldwide that is being used by haves and have-nots, by resource-rich and resource-poor? You carry it in your pocket or with you all the time. This is a great example of scale-independent technology. Challenge yourself, young minds. Close to 100 people are sitting in there. I want to challenge you. There's no dearth of talent in India. Think about disruptive technology. If somebody tells you what you're working on is not going to work, that's your approval. Because think about it, when President Kennedy said in 1960 that we're going to go on moon, I give you 10 years, we're going to land on moon. If people would have said you're crazy, we could never do that, it wouldn't have happened. But they did it in 9 years. He gave 10 years, and we did that in 9 years, right? 1969, we landed on moon, right? So this is the age of disruptive technology. Here's another thing, and I hope I'm not giving a different signal than what your Vice Chancellor may have said. Everybody knows about Harvard University, okay, or Oxford or other very big institutions. A lot of schools, we call it school or colleges or universities, when they promote on their brochure, what do they print? Oh, we have 100% placement. Sounds familiar? 100% placement or 80% placement. I'm not talking about whether that's right or wrong. That's totally right. What does Harvard say? We produce leaders. They don't talk about 100% placement. Harvard says we produce leaders. That's number one. And number two, they say we produce entrepreneurs. If you give a placement, that's one job. You create an entrepreneur, that's hundreds of jobs. Right? So that's a shift. And I think that shift is happening in India as well, where you were showing me an incubation center where you have 30 startups right now working in IoT and other. More of that is needed. Challenge yourself that what you're learning at the university, you translate into a product that people, masses can benefit. So you employ yourself, but then you start employing others. Okay? You start employing others. So be a leader. Be a leader in any space. If you see a problem, don't just complain about it. Do something about it. And challenge yourself, what is it? How can you make that happen? And the more people tell you, no, this is never going to work, that's your approval. That's your approval. That tells you that this is a major problem and we're going to do something about that. I'll just wrap up with this concept that I also shared at the keynote, because I have talked with several private companies in India, and some of them are thinking, and I think they have also already started working on this. So this is small-scale farming system. If you look at a command area, a small area, so in this case 200 some hectares, that's your city center right there. If I were to zoom in, of course, these are small-scale farming system, 1 acre, 2 acre, 3 acre fields, and they're growing rice. Okay, and this is coming from Andhra Pradesh, not too far from here. Okay, now you also have access to digital soil survey maps. If it's not digital, that can be digitized. This is something can be easily done in the GIS laboratory, or if you're a private partner, you can do that. Then based on these layers of information, just like I was talking about creating sensor nodes for our fields, because our fields are very large, here you have a farm or multiple farms where private partners are putting in sensor nodes. They're collecting information about soil, plant health, soil health, weather, humidity, temperature, all the parameters that are important for agriculture systems. So here's a good looking field, right? This is a concept. Okay, I just want to repeat it so that you guys understand. These are some of those sensor nodes with fusion sensor networks, not just one or two sensors, but a fusion of multiple sensors. And this data goes to a nearby router. From the router, depending on how often you're pinging these sensors, it goes to the cloud. And then from cloud, this is the challenge, translating data to decisions. Translating data into decisions, so that then a practitioner or a consultant, crop advisor, can show the farmer, this is the challenge, here's the pest problem, or whatever the challenge might be, or nutrient deficiency based on the sensor data. And then once you have farmer approval, you can do something about that. Completing a full cycle for a fee. Farmer is not spending money for the infrastructure, they're paying you for the decision. There's a difference. They're not paying for the infrastructure, they're paying you for the decision. This is not going to be easy. Absolutely not. It's not going to be easy. Some states, some districts, I've seen it personally, where they're acquiring data through UAVs. I was in Punjab earlier this week, and then they're running through this routine and using these larger spray drones to apply exactly what I'm showing. It will require an army of young entrepreneurs. I'm not talking about graduates, I'm talking about young entrepreneurs, an ecosystem of well-funded agri-startup. I know there's an institute here on agribusiness, I think they call it Manage, if I'm right. That's producing a lot of agribusiness startups. They're very proud of that. I'm sure this institution is doing that too, but you need to do more. You need to do more to be able to translate the challenge into that piece of information. How am I doing on time? I think it's about 12:41. Okay, so I'm just going to wrap up right here and open the floor for questions. I hope I have planted some seeds in your mind. Again, I want to repeat that it looks exciting to be working with technology, but it's not the technology that's a solution. It's translating the data into information, developing robust algorithm that requires a lot of mathematical background, okay? And then going from there to decisions so that the farmers can actuate. Thank you so much.